My name is Akihiko Chiba with IMR, Tohoku University. Very pleased to be here to have a presentation in front of all of you online. But prior to my talk, I would like to appreciate the organizer of this workshop. It's a very nice workshop. Today, I would like to talk about here a significant alloy powder characteristic for powder bed fusion type electron beam additive manufacturing, so-called 3D printing technology for metal. The collaborator for this research here, you can see Kenta Aoyagi, Yufan Zhao, and Kenta Yamanaka, and also all of the members in my research laboratory. Yes, these people are the staff of my laboratory. Yeah, sorry. Sorry. Here, in this talk, I will provide a topic on, of course, electron beam additive manufacturing, abbreviated by EBM technology. It provides a topic on the property of alloy powder, which have a significant effect on building quality. In this abstract, you are confusing now. Two topics will be presented, but today's presentation will focus on one topic. I will, due to time limitation, I will present powder characteristic and part quality. That is powder morphology in defect suppression of additively manufactured Inconel 708. As you might know, the additive manufacturing is an emerging technology that can produce metallic components with complex geometry, meanwhile saving the developing time, lead time, and component weight as well. Our laboratory is focusing on the study related to the powder bed fusion with electron beam, which is called PBF EB abbreviation. So in PBF EB, the building process is carried out under a clean and controlled vacuum environment instead of air filled by the argon gas or nitrogen gas, just using a vacuum environment. So powder bed is kept at the high temperature to avoid powder smoke. It's a very detrimental effect to fabricate the parts in EBM process because powder abruptly spread out just after electron beam irradiation. So we need a heating process. It's a very something like a drawbacks instead totally different from laser beam SLM process. But this is an introduction slide. But a recent researcher have suggested that the characteristic of the metric powder feedstock played a significant role in determining the process stability and repeatability. Especially here you can see here we can see powder morphology affect powder flowability, spreading uniformity, and packing density of the powder layer. And here, reused powder typically bring about quality reduction in particle sphericity, surface roughness, and internal porosity. Therefore, there is a demand to know precisely how the powder morphology affects the forming quality of PBF built component, which is object of this talk. Okay. So here, this is the slide method. In the present study in Inconel 718, samples were fabricated using two powder producing methods. It's a very well-known gas atomization process, and not so well-known PREP, standing for plasma rotating electrode process, abbreviated by PREP. So GA, okay, gas atomization powder, abbreviated by GA from now on. GA process easily produces powder with satellite particle and a relatively large surface area due to the shape irregularity. And gas entrapment during solidification contribute to the pore formation like this here in this powder. This is one of the detrimental effects for gas atomization process. But on the other hand, here plasma rotating electrode process PRP process produces spherical powders with considerably high roundness and low porosity. Almost no porosity inside the powder in the PREP method. This study focusing on the powder characteristic, especially powder shape on the solidification behavior. So the two types of powder, GA powder and PREP powder have almost the same particle size distribution, abbreviated by PSD, which minimize the effect of particle size on the result. Here, this is a slide showing the circularity for GA red line, and the PREP blue curve versus particle diameter. As you know, as you can see here, the very high sphericity for PREP powder compared to the GA powders. This is a very good characteristic of the GA PREP powder, totally different from GA powders. Okay, so notably, as powder particle undergo a thermal interaction with an electron beam, of course. Here shows the discrete element method, DEM, to simulate the powder bed making for powders. And also mesoscopic numerical simulation for melt pool were applied to analyze the fusion process on powder layer composed of two types of powder, thereby verifying the significance of powder characteristic in defect suppression of EV-PBF built in Corner 718. This is a, as you can see, this is a melt pool simulation by using a CTFD method. We can understand the thermal distribution in the melt pool and fluid flow velocity inside the melt pool by using this kind of fluid dynamic simulation. A very effective way to know the thermal distribution, temperature distribution in the very localized melt pool. This gives us the thermal gradient and also the solidification velocity. It's a very important parameter for solidification behavior of melt pool. Result in total PBF-EBM process. Okay, and also this slide shows how to find out the process window for each powders. Yes, after characterizing the surface profile here and the density of each sample fabricated using GA powder and the PRP prep powders, the process map for both types of powders were established. Here you can see a process map using a machine learning method. There are fewer green spots representing a dense and even a sample built with a GA powder than that was a sample built with a PRP powder. A green area corresponding to the good process window compared to the process window in the GA sample, we can find a narrower process window in the GA samples. So this shows it is respective of whether the energy input tend to be insufficient or excessive. And the PRP powder shows better adaptability than that of the GA powders. Okay. And also the slide, the slide shows the relationship between the density of the build sample and the heat input here. Horizontal axis sample built using PRP powder saturate at the lower heat input and settle to a density value of approximately 8.25. On the other hand, the build sample using GA powder here, blue one, shows saturation of density with a larger heat input and become 8.2 density. Okay. This is a lower value than the sample built using PRP powder. This indicates that the use of PRP powder enable high density building with lower heat input. Here you can see again, GA powder has a irregularly shaped particle, including sometimes gas buoys like this. On the other hand, PRP powder shows a very spherical, and the roundness is very good without any gas porosity inside the powders. Okay, so this characteristic of powder result in the density, quality, high quality of build samples. Right, and generally the most suitable processing parameter may vary depending on powder types. Therefore, the optimal processing condition for both type of powders were obtained through a sample machine learning based approach produced by our research group. Okay. Seen from the binarized SEM images, there were gas pour here, block 1, and buoys in the sample built with a GA powder. Spherical gas pour with larger size came from the powder, probably, but such a pour was absent in the sample built with PRP powder here below. So it is worth noting that there are some elongated, irregularly shaped buoys in the sample built with the GA powder, these boys are arranged along the building direction and were distributed in the interdendritic region. Here, you can see such kind of interdendritic boys was almost absent in the sample with PRP powder. It's a very surprising to see in the from the result. It is considered to be caused by inappropriate melting and solidification condition in the local region and act as a crack initiation during the service of component here. So, okay. And also, this is a simulation result, help to analyze the consolidation of the powder layers here. Okay. In the DM simulation used for modeling the dynamics of non-spherical powder with attaching satellite particle and irregularly shaped, the particle clamping method was applied in this simulations. Here, we can use this method to create powder bed formation with irregularly shaped powder. From the CTFD simulation, melt pool profile, more uneven surface profile was observed was a GA powder here. Compared with that for the PRP powder layers. And this surface area and porosity of the packed powder layer were different, thereby giving rise to different heat transfer properties. This is a simulation result. But actually, this is an experimental result after simulation, but result is very consistent. Experimentally determined surface profile for PRP left and GA powder right of Inconel 718 after single track melting was similar to those obtained from the simulation previously mentioned. Based on simulation result and theoretical analysis, low energy absorption rate and thermal conductivity made the GA powder likely to evoke lack of fusion and excessive melting under low and high energy conditions respectively. Here you can see the boring effect after the beam scanning. Here we can see the large amount of boring defect inside the melt track. On the other hand, in the case of PRP powder, a little bit we can find, but almost the melt track is very sound. This comes from the difference in powder characteristic difference. Consequently, processing with PRP powders had a broader process window than GA powders. This is a very good advantage for powder technology used in additive manufacturing. Summary: GA powder has a high emissivity and a lower thermal conductivity, result in lower energy absorption rate, and this become to the over melting under high energy input, as well as lack of fusion defect formation under low energy input. Processing with PRP powder has a broader process window than GA powder is a very interesting and very impressive conclusion in my research topics. And also, this is a microstructure observation result. Here, no concerning the internal defect. Generally, these voids here, a GA sample has a large amount of voids and carbide and lattice phase. On the other hand, there is no defect for PLP powders. Okay, this is a tendency of shrinkage formation is influenced by the density of the solid phase. Here is the formation. A solid phase density is rho S, and the liquid phase density rho L of an alloys. In particular, the density of the principal constituent element, niobium, titanium, and chromium and carbon of these two interdendritic phases are all lower than that of the matrix element nickel. Therefore, the great segregation degree in the interdendritic region promotes the possibility of interdendritic shrinkage. Okay, here, this is a slide showing the role of powder morphology in internal defects. The suppression of internal interdendritic voids forming in the sample built with the PREP powder was due to the high cooling rate and solidification rate evaluated by numerical simulations. Yeah, due to the high energy absorption rate, the fusion of the PREP powder layer produced a deeper molten pool than that of the GA powder layer. Okay, here, and the deep molten pool creates a small angle between V and R. V means velocity of beam scanning, and R means solidification velocities. And so this smaller theta gives us larger R solidification velocity R. As a result, liquid easily flowed into the interdendritic region like this to compensate voids and significant segregation tendency made the solid and liquid density closer, which in turn restricted as interdendritic shrinkage formations. Okay, so this is my conclusion. Processing with prep powder has a relatively broad process window, suppressing defect, irrespectively on whether the energy input tend to be insufficient or excess. PREP powders showed better adaptability than GA powder. Compared with PREP powder, besides gas or formed by the gas entrapment in GA powder, a lot of interdendritic voids in the GA sample, even with optimal processing conditions. Lastly, low energy absorption rate and thermal conductivity made GA powders likely to evoke lack of fusion and excessive melting under low and high energy conditions, respectively. Lastly, the suppression of interdendritic voids forming in the prep samples was due to the high cooling and solidification rate. Thank you very much for listening.